This is the second tutorial on doing cluster analysis within ArcGIS 10.2. In a previous tutorial, we looked at using the cluster and outlier local statistic to identify clusters within emergency calls in the Fort Worth area. In this example, we're going to be looking at Polygon attribute data values to do the same kind of analysis, although working with slightly different data. So for this tutorial, we're going to be working with map 9.2 from the data that should be available from the Canvas website. So I'm going to open up that map document 9.2, and here we're working with census data from Tarrant County, and we're looking at a scenario, an economic analysis scenario, where we're trying to identify two different types of communities for different reasons. So in this case, the Tarrant County Economic Development Office is interested in doing outreach and fundraising work, and so they want to target communities with higher median incomes so that they can focus their efforts there. At the same time, they're looking for communities that have low incomes so that they can target their efforts there, or target the development efforts there so that they can place more services in those particular communities. So the data we're working with, as I said before, is the census data, and if you take a look at that data here, you can see the kind of data that's available and what we're working with. The attribute value that we're particularly concerned with in this case is this P053001, which is the median income values for each census tract. So that's what we're working with, and we're working with a little over 1,000 census tracts here, so it's quite a bit of data. I'm going to switch over to data view here so we can see the data a little more closely. So you can visualize the data pretty easily by simply classifying it according to that particular attribute value that you're interested in. So in this case, if we used the median income value and then picked some kind of symbolization scheme, we can see the variation in income across the area, and these show where there are higher incomes, and you can already see that there are some areas where you have groups of census tracts that have higher or lower incomes. So you can see an apparent pattern in there, but as we've learned previously, that pattern can be very subjective, because it can be controlled very much by the way that you classify the data. So in this case, for example, if I went to the properties, and right now it's defaulted to the natural breaks, if I change the classification scheme to a different classification scheme like equal interval, which is probably more intuitively understandable, you'll see a slightly different pattern, and so the extreme apparent differences seem to kind of fade quite a bit. And here, working with the same data again, it's just a function of the way that you classify the data. So how are you to identify then some significant clusters? Well, that's exactly why you turn to a statistic or a cluster analysis statistic to kind of find and tease out those areas. So here we're going to work, I'm going to use two. We're going to use the local Anselin-Moran's eye cluster and outlier tool, and we're also going to use another one, the GEDISORD GI star statistic. So we're going to open up the Spatial Statistics Tools toolbox, and within the mapping clusters, we're going to find the two tools that we're interested in. So we're going to start with the cluster and outlier analysis, Anselin Local Moran's eye, which we used previously to work with the feature attribute points for the emergency calls. So I'm going to open that up, and in the dialog window that pops up, we have a few choices to make. So clearly, the input feature class is the one that contains the income data. The input field is going to be that attribute field that has the median incomes, and it's going to produce an output, which is going to be another feature class that contains the visualization of the hotspots, or the hotspots. So we're going to call this the income local Moran. It takes a second to accept that. Okay, there we go. And then we're asked to conceptualize the spatial relationship. And here, this one's a little different. You can always choose, you always have a variety of choices in terms of how you want to specify the spatial relationship. And essentially what this says, it tells the computer how to define the neighborhoods around any individual feature. So how far should it look out? What kinds of features qualify as neighbors to any given feature, And so you can define neighborhoods essentially around which to do the analysis in order to identify hotspots in a couple of basic ways. One is to do it in terms of distance, and you can specify how distance changes or how distance is affected. For example, with inverse distance, you're looking at a situation where things that are closer have a bigger influence than things that are further apart. And that makes a lot of sense for things that are like points, for example. But with polygons, it's a little more complicated because you have a variety of irregularly sized features, and because the sizes of them vary, distance isn't quite as straightforward as it is with points because you're measuring across polygons. So in this case, one of the typical ways that you deal with polygons is to work with contiguity rather than looking at distance. And contiguity essentially says that polygons that touch one another qualify as neighbors. So when the analysis is done, any polygons that touch are going to be counted. And you have two choices there. You can choose edges only or edges and corners. So we'll be generous and we'll say edges and corners in this case, right? When you choose that particular option, you'll see that the distance method is grayed out because it's not relevant in this case. And here we're going to be interested in this option for row standardization. And what row standardization does is it accounts for the fact that some polygons are going to have more neighbors than others. And we don't want that to necessarily influence the relative impact on the statistic, because the number of neighbors is likely to be a function of the size of the polygon. So there's smaller polygons that'll have more neighbors, as well as the possibility that when you're looking at the edge of the analysis area, polygons that are on the edge of the analysis area will have fewer neighbors, and so you don't want that to influence the outcome of your result or have too big of an impact. Lastly, you have the option to apply a false discovery rate, which corrects for redundancy in the computation of the statistic. Again, taking into account, as I described in the previous tutorial, the fact that neighbors are counted repeatedly because the neighbor of one point is also the neighbor of another point. So this is what we want. We've specified the attribute value that we want, and we're going to have an output, and we're going to do contiguity with edges, and we're using row standardization. So hit OK, and it's going to compute the statistic, and it's going to produce a new feature class. It's going to look like the original feature class in terms of the polygons, but it's going to also produce the p-values, the z statistics, and also the Moran's I indices or index numbers that you can interpret directly, or you can work off of the way that the automatic symbolization scheme that it's going to apply in this case. So again, it might take a second because it's got to compute it for all polygons. Okay, so it ran. We got a nice clean result, green check mark, which means there were no concerns with this data set. You can always click on it and it shows you the results of that process in terms of what it produced. But in this case, the results are demonstrated to us. So what we have here then in the output is the computation of the areas that showed significant clustering as well as outliers. So just like with the point data, gray areas represent areas that weren't significant. They didn't show any statistically significant tendency, or they weren't statistically significantly different from a random arrangement of values that you would expect if you were to reassign the attribute values across this area randomly. The black areas show areas where you have high values clustered next to other high values. So clearly here, if we were targeting for our fundraising, these are the high income clusters of neighborhoods that we would want to target for that. The blue areas represent the census tracts where you have clusters of low values next to low values, and so this implies these are communities that probably need a little more resources devoted to them, so that's maybe where you would target your development efforts. The orange and white areas, there aren't any orange here, but we do have a white area right there and one over here as well. The white areas indicate that you have a census tract with a low value surrounded by other census tracts with high values. So you see again this juxtaposition of differing values. So that's how you interpret the local Moran's I local statistic for cluster analysis and outliers using polygon data, again using with contiguity. We can do the same analysis using the hotspot analysis Getasor GI star statistic. So this one, we'll start that up and we're going to run it as well. It's going to ask you for a few input features. So again, we're going to put in the census tract data that contains the income, again specifying the median income. Once again, we're going to produce an output, and so this time we'll call it income instead of local Moran. We're going to call it GEDIS ORD. Okay, and we'll save that. And then conceptualization of spatial relationships. Again, because we're working with polygons, it's probably appropriate to use contiguity rather than distance. So we'll use contiguity with edges and corners again to make it consistent with the previous analysis. Okay, and when you do that, again, you'll see that the distance method is grayed out, but you'll also see that standardization is grayed out, and that's because in this particular statistic, the number of neighbors doesn't affect the computation of the index that's being used in this particular case. So this particular cluster statistic is not influenced by that, so we don't have to worry about that. Again, a couple other options. Well, one other option with the self-potential field. We're not going to worry about that for the moment. Again, you have the option of applying the false discovery rate to account for redundancy in the data analysis. We'll leave that off for the moment. So we'll hit OK and let that run. Okay, statistic ran. Again, green light on the outcome of the hotspot analysis, right? So what we're looking at here is a hotspot analysis, and in this case, the blue areas are cold spots, represent areas where you have low values next clustered around low values, and then the red areas are areas where you have high values clustered to high value areas, and then the well, I guess beige, pink, it might depend on your computer, areas are not significant, so they didn't qualify as significantly different from random in this statistic. Now, the nice thing in this particular statistic is that you see that you get different ranges of confidence. So depending on the analysis that you're doing and the level of confidence that you want in rejecting the null hypothesis of randomness, you can look at the data that way. So the darker blue areas have the highest confidence and deviate the most from the random assumption, and similarly with the red values. What you don't get here in the GEDIS or GI star statistic is you don't get the outliers. So that is not pulled out in this particular analysis. So if you need that, or you were looking for that, then obviously you would turn to the Ansel and local Moran's I local statistic. So the two processes, the two statistics, as you can see, generate very similar results. You can see that for the most part, the hotspot or the clusters or hotspots essentially occur in the same places, so there isn't too much deviation there, but you're provided with a slightly different kind of presentation of the information, and both essentially get you to the same location, so then you can proceed with your analysis and begin looking for ways of describing what you're seeing here, as well as looking for doing further analysis to find out why this has happened.